Good day, everyone. In this video, I will going to discuss the second part of analytic trigonometry. This is all about the trigonometric equations. We're going to solve for the angle given a trigonometric equations. The takeaway or your takeaway for this lesson is that you will be able to solve trigonometric equations. Now, the first part, I will going to discuss the different ways to analyze trigonometric equations. These are very useful in order for you to what to do when dealing with trigonometric equations. How are you going to modify those expressions so that you will come up with very simpler equations. And with that, you can simply take the inverse and find the angles. But take note, in trigonometry, there are lots of values for sine, cosine, and tangent that exist uh, for, or there are lots of angles for sine, cosine, and tangent for a certain value. Say, for example, for 1/2, the arc sine of 1/2 is 30 degrees, but that is also the same as sine of 390. That will also give you 1/2. So there are lots of uh, angles that if you're going to take its sine will give you 1/2. So you have to take that into account when dealing with trigonometric equations. So here there is no single that applies to all trigonometric equations, but the following strategy will help us to solve them. The following strategies, by the way, this one. So these are the strategies that I can recommend to you. First is always remember of the solutions to the simpler trigonometric equations. Sine x equals to a, cosine x equals to a, and tangent x is equals to a. You can solve directly for x in this equation by taking the arc sine. So you have x equals to arc sine of a. Then for this equation, you have x equals to arc cosine of a. Then for the last, you have x equals to the arc tangent of a. Next, solve an equation involving only multiple angles as if the equations had a single variable. And number 3, you can use identities to simplify complicated equations. So don't forget those trigonometric identities uh, that I have discussed from the previous video. So try to get an equation involving only one trigonometric function. And number 4, as much as possible, apply factoring to get different trigonometric functions in separate factors. Then use factoring or quadratic formula for equations of quadratic type. So there are some cases that you're not only given with linear trigonometric equations. There are times that the degree of the trigonometric identity is 2. So we are going to model that one as a quadratic equation. Then number 6, if necessary, apply squaring both sides of the equation so that identities involving squares can be applied. So check your answers always. So check for any extraneous roots because there are some cases that uh, what you get is not really part of the solution of the trigonometric equation. So you have to check that one. Now let's proceed to the cosine equation. So the form cosine x equals to a, where a is a number in the interval from -1 to 1 inclusive, is the most basic equation that involves cosine. So recall that the range of values for cosine x is on the interval -1 to 1. So it will not go beyond 1, and it will and also for -1. So it will stay from -1 to 1, including -1 and 1. Then the next, the period for cosine x is equals to 2 pi, which means that uh, if you have an angle of 30 degrees, so the cosine of 30 is square root of 3 all over 2. If you're going to rotate that one by a one full revolution, the value of the new angle is still equal to the cosine x, because when we say period, that is the um the the periodic behavior of a cosine such that the value of its angle are still the same. We can visualize that one to our uh, cosine graph. So this is the graph of our cosine, and this one right here is the period. So the time we're in, the initial value of cosine that is right here is equal to the next. Okay, so the length of this one is 2 pi in terms of its angle. So the formula for the period, if you have cosine of x, that is also equal to cosine of x plus n 2 pi, where in n is any integers. It could be 0, plus or minus 1, until so on and so forth. So if you have, again, cosine of 30, that is also the same as if you add or you make one a full turn after 30 degrees. So that would be cosine of 390 degrees. If you're going to input this one in your calculator, that will give you the same value for your cosine. So that is how period works for cosine. And don't forget to remember this one. This is very useful when solving trigonometric equations. Now let's have some example. So example number one, solving a cosine equation. Find all real numbers that satisfy the equation cosine x is equals to 1. So one of the solution for x is by taking the inverse cosine of 1. So cosine x equals 1, take the inverse, so x equals to the arc cosine of 1. So the angle that will give a cosine of 1 is 0 degrees. That's one of its solution, but there are lots of solutions if we apply the period of cosine. Okay, so we can refer that analysis from our unit circle. So this is our unit circle, and this point right here will give us a cosine of an angle equal to 1. Okay, because the coordinates of this one, the unit circle, is 1 0, so our x here is 1, and that corresponds our cosine of an angle. Now the angles that will give us a cosine of 1 are 0. So 360 degrees, that's 2 pi. It could be plus or minus. So depending upon the rotation of the angle, it could be in counterclockwise or in clockwise direction. Still, it will give us a cosine of 1. And also, if we rotate more, so you have 4 pi, and next is 6 pi, then so on and so forth. So there are lots of angles that will give us a cosine equal to 1. So the solutions are indeed the coterminal angles of 0 degrees. So in equation form, that is x are all values of 2n pi, wherein our n is any integer from 0 to plus or minus 1 up to infinity. Okay, so these are the possible values of our x that will make cosine equal to 1. Okay, so this is our final answer. For number 2, solving again another cosine equation, this time cosine of x equals to 0. Again, all real numbers. We're going to find all real numbers for x. So one of the solution for x is by taking the inverse cosine of 0. So an angle that will give a cosine of 0, that's 90 degrees, or pi over 2 in radians. However, again, cosine is periodic, so there are lots of angles that will give a cosine equal to 0. And we can refer our analysis from our unit circle. This time we have 2 points that will give us a cosine of 0. That is on the upper portion. This is uh, a factor of 90 degrees. So we have plus or minus pi over 2, 5 pi over 2, 9 pi over 2. And in the lower portion, we also have the 270 degrees, or that's 3 pi over 2. Then make another one full rotation again. You have 7 pi over 2, and then 11 pi over 2, so on and so forth. So the solutions are the angles whose terminal side lies on the vertical axis. So these two on the upper portion and in the lower portion. So these angles differ only by how much? So by pi. Okay. So this one is equal to pi. And if we start right here, this is one is also equal to pi. So both angles differ by pi. So if we represent that one in equation form, we will start with pi over 2, that is 90, and then we will add 180 so that we can get the next angle that will give us a cosine of 0, and then add again pi to get the upper portion, and then add again pi to get the lower portion. That is why we use this notation right here. So pi over 2 plus n pi. Now, n here is any integer, that is either positive integer or negative integer, because if we have a negative integer, that means that if you start in this section, you will just reverse your direction and still you will arrive the the spot that will give us a cosine of 0. So this is our final answer for this equation. Again, we have lots of answers for this one. That is why we represent that one in equation 4. That is in terms of n. Okay, so where n is an integer. Now, if you don't want this notation, you can list all those um, possible angles, just like what I did in this section right here. So I list, then I just simply put the dot dot dot, because this one repeats infinitely. Okay, or this one goes infinitely. Okay. Next, we'll proceed to the sine equation. So the form sine x equals to a, where a is a number in the interval -1 to 1, is the most basic equation that involves sine. So same with cosine, the value of sine of any angle only ranges from -1 to 1. It will not go beyond 1 and -1, because that will make our calculation undefined. Now recall that the range of values for sine x is only within this interval -1 to 1 inclusive, meaning -1 and 1 are part of the range of values for sine x. Then the period for sine, same with cosine, that is equal to 2 pi. So we can prove that one by looking at the graph of sine x right here. So this is the length of the period for sine. That means that the value initially will be repeated after 2 pi, okay, right here. So if that is the case, for the period of sine, you have sine of the angle is simply equal to the sine of the angle plus another full turn, that's 2 pi or 360 degrees. Meaning to say, if you have sine of 30 degrees, that is also the same as sine of 360 plus 30, that's 390. Okay, because sine function is periodic at 2 pi or 360 degrees. So where n here is any integer. This is very useful when dealing with sine equations. Now let's have our third example. This time we will solve a sine equation. So we are going to find all real numbers that satisfy the equation sine x is equal to -1/2. So one of its solution for x is simply taking the inverse sine of -1/2. So x is equal to the arc sine of -1/2. So we will think of an angle that will give a sine of -1/2, and that is um 0. No, it's not 0. So I forgot to edit this one. The angle that will give us -1/2 for sine, that is -30 degrees. Okay, so let me let me edit this one first. Okay, so I already edited this section. Again, the arc sine of -1/2 is -pi/6. So this is -30 degrees. Okay, now in standard notation, because this angle is rotated clockwise, if it is an angle in standard position, that is the rotation is counterclockwise, starting with the positive x-axis, this will give us an equivalent coterminal angle of um, I think that's the angle is 2 pi for um, one full turn. So it will give us 11 pi over 6. So this is the angle in standard position, which is equivalent to -pi/6. Now, there are lots of angles that will give a sine equal to negative 1/2. So we already know that one. Now, if we're going to refer our analysis in the unit circle, these two spots right here will give us a sine of negative 1/2, which means that both in quadrant 3 and 4, our sine is negative. So we have these two spots. This one right here has an angle of, this is negative pi over 6. So in standard position, that will give us an angle of 11 pi over 6. So the coordinates for this one is we have square root of 3 over 2, then negative 1/2. So this is for the sine as well as this one. Now the angle for this is pi over 6. Okay. So in standard position, the coterminal angle for this one is 7 pi over 6. So we have 7 pi over 6 and 11. Okay, this one right here, this is 11 pi. It is 11 pi over 6. So from the unit circle, the angles in quadrant 4 that will give a sine of negative 1/2 are, starting with 11 pi over 6, then make one full rotation for the period. That is 11 pi over 6 plus 2 pi. That will give us 23 pi over 6. Then plus 2 pi again. That will give us 35 pi over 6. And so on and so forth. Now in quadrant 3, our second spot, the angles that will give us a sine of negative 1/2 are, so starting with 7 pi over 6, then plus 2 pi for the period, so that's 19 pi over 6, plus 2 pi again, that will give us 31 pi over 6, so on and so forth. Now you can have your answer in this form, or you can represent that one in equation form. So the solutions are the coterminal angles of these two, the 11 pi over 6 and the 7 pi over 6. So in equation form, so x are all values that will satisfy the equation, starting with 11 pi over 6 plus 2 n pi. So for 7 pi over 6, you have 7 pi over 6 plus 2 n pi, wherein n is any integer from 0 to plus and minus 1 up to infinity. So you can have your answer in equation form or in this notation. Next, we'll proceed to the tangent equation. So the form tan x equals a, where a is a number in the interval negative infinity to positive infinity, is the most basic equation that involves tangent. Now, unlike sine and cosine, the range of values for tan x goes from negative infinity to positive infinity. We can also see this one from the graph of our tangent later. So recall, so the range of values for tangent is from negative infinity to positive infinity. And then the period for tan x is equal to pi, not 2 pi. Okay, we can see this from the graph of the tangent function. So this is the graph of our tangent function. As you can see, this is asymptotic at an angle of pi over 2, or factors of 90 degrees, because tangent of 90 degrees will give us an infinity uh, expression. Okay, now this is the period of our tangent. As you can see, this value repeats after pi. Okay, so therefore the tangent of x, or any angle, is simply equal to the tangent of x plus some factor of its period that is equal to pi. So if you have tangent of 60, that is also the same as tangent of 60 plus 180. Okay, by using this one, where n is an any integer, so from 0 to plus and minus 1 up to infinity. Okay, so let's have an example for the tangent function, the tangent equation. So tangent x is equal to 1. So one of the solution for x is simply by taking the inverse tangent of 1. So x is equal to the arctangent of 1. So the angle that will give us the tangent of 1 is 45 degrees, or in radian, that's pi over 4. But of course, we all know that there are lots of angles that will give a tangent equal to 1, because tangent is periodic. We can refer our analysis from the unit circle. So in the unit circle, we have two spots that will give us a tangent equal to positive 1. because the tangent is positive in quadrant 1 right here and in quadrant 3. So this spot has coordinates square root of 2 over 2 and square root of 2 over 2. So this is indeed a 45-degree angle. Okay, this one right here is 45 degrees, and this one is also 45 degrees. As you can see, they are aligned with each other. So the difference of their angle is simply equal to 180, or that's pi in radians. So from the unit circle again, the angles in both quadrant 1 and quadrant 3 that will give a tangent of 1 differs only by the period of the tangent function that is equal to pi. So the angles in the first quadrant are pi over 4, or for both quadrant 1 and quadrant 3 can be represented by this notation. So starting with 45 degrees, that's pi over 4. And since the difference of these two locations is equal to 180 or pi, so pi over 4 plus pi, that's 5 pi over 4. Next, add again another pi, that will give us 9 pi over 4. And then add again another pi, that will give us the next angle, that will still give us a tangent equal to 1. Or you can also do the reverse. So starting with the negative, so you can also have um, this one. Okay, okay. So next, the solutions are the coterminal angles of uh, pi over 4 and 5 pi over 4. So 5 pi over 4 is located in quadrant 3, and then pi over 4 in quadrant 1. So we can represent this set of angles by using this notation. So starting with pi over 4, we add n pi, wherein n is any integer. So it could be 0, plus or minus 1, up to infinity, so on and so forth. So this is our answer in this notation. Next, we will proceed to tangent x equals to negative 1.34. So one of its solution can be determined by taking the inverse tangent of negative 1.34. So x is equals to the arctangent of negative 1.34. You can use your calculator. So x is roughly equal to negative 53.27 in degrees. But of course, there are lots of angles that will give us a tangent equal to negative 1.34. So we will refer our analysis from the unit circle. So the quadrant quadrants that will give a tangent of negative are quadrants 2 and 4. So the tangent here are negative. So for this spot, its angle measured clockwise is negative 53.27 degrees. That is the angle that we have uh, we have solved in the first place. Now this angle right here is equal to 126.73. So this was determined by subtracting 180 degrees minus this one. So this one is equal to 53.27. So 180 degrees minus 53.27, that will give us the angle in standard position of this spot, that is 126.73. Next, from the from the unit circle, the angles in both quadrant 4 and quadrant 2 that will give a tangent of negative 1.34 differs only by the period of the tangent, which is equal to pi, or 180. So it's very obvious, no? Uh, the difference of these two is equal to 180 degrees, or pi, or a straight angle. Now the possible angles that will give us a tangent of negative 1.34 are negative 53.27. Then or add some negative pi, so that will give us negative 233.27. Then minus pi, that's negative 413.27, or minus 360 degrees in radian. I don't know, minus 180 degrees, no, in degrees. Okay, so these are the collections of angles that will give us a tangent of negative 1.34. Or you can also use the positive, starting with the angle in standard position in quadrant 2, that's 126.73. Add pi, or 180 degrees, that will give us the next angle, that is 306.73 degrees. Then add again 180, that will give us 486.73 degrees. So these are our answers in this notation. But if you want your answer to be in like equation or expression form, so refer to this next step. So the solutions are the coterminal angles of negative 53.27 degrees and 126.73 degrees. In notation form, you can start with the negative 53.27 degrees, then you add 180 degrees because both of these two locations differ only by an angle of 180 degrees. So we have here 180 n degrees, wherein n is any integer starting at 0, then plus and minus 1 to infinity. Now, if you're going to input these values right here for both positive and negative, you will arrive these two sets of angles. Okay, so you can also have your answer in this notation right here. Next, we'll proceed to the sine equation involving a double angle. So determine all the solutions in degrees. In the equation, sine 2x is equals to 1 over square root of 2. By the way, 1 over square root of 2 can also be expressed if we're going to rationalize the denominator. This is also equal to square root of 2 all over 2. So one of the solution for 2x is by taking the inverse sine of 1 over square root of 2. So 2x is equal to the arcsine of this expression, and the arcsine of square root of 2 over 2 or 1 over square root of 2 is equal to 45 degrees or pi over 4 in radians. Again, 2x is equals to 45 degrees. However, we all know that lots of angles for 2x that will give us a sine equal to 1 over square root of 2. Now, we will refer again our analysis from the unit circle. So the quadrants that will give us a sine of positive 1 over square root of 2 are quadrants 1 and 2. So in quadrant 1, this is 45 degrees. Then in quadrant 2, this is 90 plus 45. That will give us 135 degrees. So we have two spots. So from the unit circle, we found out that the angles in both 1 and 2 give a sine of 1 over square root of 2, a positive value. And uh, these two differ only by a period of the sine, for which it is equal to 2 pi or 360 degrees. So in order to get the coterminal for 45 degrees, we can add 360 degrees. So for the 45-degree angle, you may start with the positive. So 45 plus 360, that will give you 405. Then plus 360, that will give you 765. Or you can also reverse the direction of the angle. So starting with 45 minus 360, that will give you negative 315, then negative 675, so on and so forth. So you can have your answer in this way. But not only that, since we also have the 135 degrees, so for 135 degrees, you can add plus 360, that will give you 495, so on and so forth. For the negative angle, you can subtract 135 degrees by 360, and that will give you a set of negative coterminal angles for 135 degrees. So you can also have your answer in this way or in expression form. So for the next step, we found out the solutions are the coterminal angles of 45 degrees and 135 uh, degrees. So we have here 2x. By the way, in this part, this is not yet the final answer. It's because these angles are just equal to 2x. But our job or our task is to solve for x. So you need to divide these fractions by 2. So here we have 2x equals to 45 degrees plus n times 360 degrees. So the period of sine, and also with the 35 or the 135 degrees. Next, divide both sides by 2 to solve for x. So you have x equals to 22.5 degrees plus half of 360, that's 180 degrees times n. Then for the 135, divide by 2, that's 67.5. Then plus n times 180 degrees. So where n here is any integer from 0, then plus or minus 1, plus or minus 2, so on and so forth. Next, we have a tangent equation involving multiple angles. So determine all the solutions in the equation tangent of 3 theta is equal to negative square root of 3 on the interval 0 to 2 pi exclusive. Which means that 0 and 2 pi are not part of the interval. Now, since we are given with an interval, so we are only limited with our angles within this range. So we'll not consider all the angles outside 2 pi or beyond 2 pi or beyond 360 degrees. So one of the solution for 3 theta is by taking the inverse tangent of negative square root of 3. So 3 theta is the arctangent of negative square root of 3. So the angle that will give us a negative square root of 3 for tangent is a negative 60 degrees, or in radian that's negative pi over 3. Now this is not yet the final answer because we still have lots of angles that will give a tangent equal to negative pi over 3. So we are going to refer our analysis from the unit circle. The quadrants that will give us a negative answer for our tangents are quadrants 2 and 4. Okay, so in quadrant 4, the angle for this path is negative pi over 3, or negative 60 degrees due to its clockwise rotation. Then this one right here for the spot in the second quadrant, this is 2 pi over 3, in a sense that this angle is pi over 3, and then this one is pi, so pi minus pi over 3 will give us 2 pi over 3. So from the unit circle, the angles in both quadrant 2 and 4 that will give a tangent of negative square root of 3 differs only by the period of the tangent function, which is equal to 180 degrees or pi. So this one right here, their difference is simply equal to pi. So the possible angles are negative pi over 3. Then we will add pi, so that's negative 4 pi over 3. Then another pi, or another negative pi, that's negative 7 pi over 3, so on and so forth. Or you can also start with the positive angle in standard position, that's 2 pi over 3. Add pi, that will give you 5 pi over 3. Then another pi, that's 8 pi over 3, so on and so forth. So these are the values of our 3 theta, not yet the theta. Okay, so the solutions are the coterminal angles of these two angles, negative pi over 3 and 2 pi over 3. So since the given interval is from 0 to 2 pi exclusive is positive, so we will only consider the smallest positive angle, 2 pi over 3, not the negative pi, because the given interval are all positive. Okay, the values within the interval are all positive. So we have here 3 theta is equals to 2 pi over 3. We will use this one. Then we will add the period of the tangent, that is pi. So we have plus n pi. Then divide both sides by 3 in order to solve for theta. So you have theta is equals to 2 pi over 3 times 3 is 9. Then plus n pi over 3. Next, the values of theta must be between 0 and 2 pi. That is the given interval. So therefore, we only have 1, 2, 3, 4, 5, 6 possible values for our n. And uh, and these are 0, 1, 2, 3, 4, and 5. Now we're going to generate the values of theta using the values of n above. So the values of theta are using the values of n. So you have for 0, you'll have 2 pi over 9. Then for 1, you have 5 pi over 9. Until for number 5, for n is equal to 5, you have 17 pi over 9. 17 pi over 9 is still less than 2 pi. Okay, now if we add one more angle, so it will be greater than 2 pi. So these are the only angles that will satisfy the given interval. Next, an equation solved by factoring. So determine all the solutions in the equation sine 2 theta is equal to sine theta on the interval 0 to 2 pi. This time we're given with an interval in which 0 is included and 2 pi is not included. So is included in the sense that it uses this brace rather than the parenthesis. Okay, first is you are going to modify the equation into either of the form of sine theta equals a or cosine theta is equal to some constant. Now, our given equation, uh, the right side is not a constant but a trigonometric expression. So therefore, we're going to modify this one first. So we're going to use the double angle identity for sine because we found out that we have a sine 2 theta, which is a double angle identity expression or trigonometric identity. So we have sine 2 theta. We'll know that that is equal to 2 sine theta cosine theta. So from our equation, sine 2 theta equals sine theta. So substitute the double angle identity. This is 2 sine theta cosine theta equals sine theta. Plus, if you're dealing with trigonometric equations, do not cancel out sine theta and sine theta in the left and the right side because we still need to evaluate the angle of that trigonometric identity. So in order to correct that one, so you have to transpose this on the left side of the equation so that we can factor out the sine theta. So we have here 2 sine theta cosine theta minus sine theta equals 0. As you can see, uh, we have two terms on the left side of our equation, and there's a common expression for the two terms, and this is sine theta. So factor out sine theta. What's left is 2 cosine theta minus 1. Then equate each factor to 0 because we have two factors. So for the first factor, we have sine theta equals 0. Now, one of its solution is theta is equal to the arc sine of 0. So the angle that will give us a sine of 0 is 0 degrees. However, there are lots of angles that will give us a sine equal to 0. If we refer our analysis from the unit circle, these two spots will give us a sine of 0. And these are the 0 degrees and the pi, okay, or the 180 degrees. So we can represent our theta in terms of n pi or factors of pi. However, the values of theta must be positive and between 0 and 2 pi only, including 0. So therefore, our n here starts from 0 and then ends in 1, not in 2 because 2 pi is not included anymore for its solution. So we only have theta equals 0 and theta is equals to pi. Next, we will proceed to the second factor. So the second factor is 2 cosine theta minus 1 equals 0. Transpose -1 to the right side and divide both sides by 2. So you have theta equals the arc cosine of 1/2. So the angle that will give us a cosine of 1/2, that's 60 degrees or pi over 3. But of course, we'll know that there are lots of angles that will give us a cosine equal to pi over 3. If we refer our analysis from the unit circle, the cosine that will give us 1/2 can be found in quadrants 1 and 4 because in these quadrants the cosine is positive. So for the first spot in quadrant 1, the angle here in standard position is pi over 3. Then for our spot in the fourth quadrant, the angle for this one in standard position is again 270 plus um or 360 degrees or 2 pi minus pi over 3. That will give us 5 pi over 3 because this one right here is pi over 3, and then the one full revolution is 2 pi, so 2 pi minus pi over 3, that is 5 pi over 3 as shown right here. So if we're going to implement this, theta will be pi over 3 plus n 2 pi, or since we have 2, so for pi over 3 this one, then for 5 pi over 3 that's plus n 2 pi since sine or cosine function is periodic at 2 pi. Next, the values of theta must be between 0 and 2 pi only, including 0. So therefore, our n must be limited up to 0 only, not 1, because it will be greater than 2 pi. Okay? So the values of theta are, we have theta equals pi over 3 plus 0 times 2 pi. That will give us pi over 3 and 5 pi over 3 when n is substituted by 0. Now combining the results for the first factor, so we have 0 and pi for the first factor, and then for the second factor we have pi over 3 and 5 pi over 3. So therefore these are the angles that satisfies our equation and conform to our interval from 0 to 2 pi including 0. So this is our final answer. Next, example number 9, an equation of quadratic type. So the problem statement is determine all the solutions in the equation. So we have 6 times cosine of half angle x over 2 square minus 7 cosine half angle plus 2 is equals to 0 on the interval 0 to 2 pi, wherein 0 is included. So for this type of trigonometric equation, we are going to transform this into a quadratic equation by letting cosine half angle x over 2, since this is the trigonometric identity that is being squared, so we're going to let that one by y. Therefore, the resulting equation from this equation will become 6y squared minus 7y plus 2 is equals to 0. So once we have generated the quadratic equation, next is you can apply those techniques in solving for quadratic equations. You can have completing the squares, quadratic formula, or simply factoring by trial and error. So for this example, this can be done by factoring. So we'll factor the left side completely. The factors are 2y minus 1 and 3y minus 2 is equal to 0. Then equate each factor to 0. So starting with the first factor, that's 2y minus 1 equals 0. So we have our first value of our y that is equal to 1 half. And for the second factor, that's 3y minus 2 equals 0. So we have our second value for our y that is equal to 2/3. Next, we're going to substitute back the expression of y in order to solve for x. So earlier, we let y equals cosine x over 2. So this time, starting with y1, we have cosine x over 2 is equals to 1 half. So x over 2 is the arc cosine of 1 half. That will give us x over 2 equals pi over 3. We all know that there are lots of angles that will give us a cosine of pi over 3. So if we try to refer from our unit circle, we have two spots that will give us a positive cosine of 1 half. So these are in quadrant 1 and in quadrant 4. So we have here the pi over 3 in quadrant 1, and we also have the 5 pi over 3 in quadrant 3. This is in standard position. This is 5 pi over 3. It's because this one right here is negative pi over 3. So if we have 360 minus pi over 3, that will give us 5 pi over 3. So the possible uh, answers for the angle, since it is only limited from 0 to 2 pi including 0, so these are pi over 3 and 5 pi over 3 and nothing else. Next, we're going to multiply both sides by 2 so that uh, we can arrive a solution for x. So we have x equals to 2 times pi over 3, that is 2 pi over 3, and then 2 times 5 pi over 3, that will give us 10 pi over 3. So uh, these are the values of our angle for the first factor. We will proceed to the second factor. So the second angle, by the way, is we still need to evaluate this one first. Since we multiply 2, there are some changes for the values of the angle. Maybe one of this angle exceeds the 2 pi, okay, the limit of our interval. Okay, since the second angle, the 10 pi over 3 is not included because it is more than 2 pi. If we're going to simplify this one, if we're going to convert or transform it in decimal form, this is more than 2 pi because 2 pi is roughly 6 point something. So the value of x in the first factor is only 2 pi over 3. Next, for the second factor, you have cosine, or for the second value of y, you have cosine x over 2 is equal to 2/3. Taking the inverse of the cosine of 2/3, our x over 2 is roughly equal to 0.8411. By the way, this is not in degrees but in radians. Now, we all know that there are lots of values of our angle here, not only 0.8411 radians. If we try to refer our analysis from the unit circle, so the cosine that will give us a positive 2/3 can be located on quadrant 1 and quadrant 4. So this is our angle 0.8411 in radians, and this one right here is 5.4421. That is a difference of 2 pi and 0.8411. So that's 5.4421. And since our interval is from 0 to 2 pi, including 0, so we are only um, we're only aftering with 0.8411 and 5.4421. Nothing more or nothing beyond this value. Next, we're going to multiply both sides by 2 so that we can solve for x. So x equals to 1.6822 and 10.8842. Now, the second angle, which is 10.8842, is not included because it is more than the given interval 2 pi. 2 pi is most nearly equal to 6 point something, and that is less than the second angle. So therefore, for the second factor, the value of our x is only equal to 1.6822. Now combine the results. The possible values for our x in this equation are 1.6822 in radians and 2 pi over 3 in radians. This is our final answer for this example. Next, we will proceed to our last example. This is an equation solved by quadratic formula. Determine all the solutions in the equation. Cosine x squared minus 0.2 sine x is equal to 0.9 on the interval 0 to 2 pi, including 0. So the first step, modify the equation so that it will contain only a single trigonometric function. As you can see, although it is uh, more likely in quadratic equation form, but still we need to convert this cosine x into sine x because um, one of its term contains sine x. Okay, so it is impossible or it is very difficult to convert sine x alone into like some cosine x. Okay, so the best way here is to convert cosine x squared into sine x squared using the Pythagorean identity, and that is a much easier choice. Okay, so use Pythagorean identity. We all know that cosine x squared is equals to 1 minus sine x squared. The equation that is expressed in this form becomes 1 minus sine x squared minus 0.2 sine x is equals to 0.9. Now we are going to um, multiply both sides by negative, okay, by -1. So we have here positive sine x squared plus 0.2 sine x minus 1. And then if we're going to transpose 0.9, so after we multiply with negative on both sides, this will become negative 0.9. But when transposed on the left side, it will become positive 0.9. So simplifying further, we have sine x squared plus 0.2 sine x minus 0.1 is equal to 0. So in this form, we are now ready to use or to model this one as a quadratic equation because the trigonometric identity that is present uh, are already uniform. So in terms of sine x, now each term or the two terms contains sine x, and this is already okay. Now we let y is equal to sine x, and the resulting equation becomes y squared plus 0.2y minus 0.1y is equal to 0. Now, since from the given coefficient and constant, we cannot do factoring by trial and error in this case. So we will use the quadratic formula. The quadratic formula, as you can remember, y is equal to negative b plus and minus square root of b squared minus 4ac over 2a. Now our a here is equal to 1, our b is equal to the coefficient of y, 0.2, and this is our c, which is the constant, negative 0.1. So we have negative 0.2 plus or minus square root of the expression inside the radicand all over 2 times 1. Simplifying this further, you will have y is equal to negative 1 plus or minus square root of 11 over 10. So we have two values for our y. So our y1 is negative 1 plus square root of 11 over 10. That is roughly 0.2317. Then the second value for our y is roughly equal to 0 Now for the first root y1, so we take sine x. We will substitute this back to our first first um, assignment now for y. So we let y is equal to sine x in the first place. So we will substitute the value of y back then. So sine x is equal to 0.2317. Take the arc sine. So we have x is roughly equal to 0.233 radians. So this is in radians. Be careful. Next, we all know that we have lots of angle that exist for sine x equals 0.2317. We can prove that one from our unit circle. So we have two spots that will give us a positive value for our sine. These are in quadrant 1 and in quadrant 2. So in quadrant 1, the angle here is 0.2338, whereas in quadrant 2, simply take the difference of pi and 0.2338, because this one right here is 0.2338 and we have a 180-degree angle. So the angle here for the second quadrant is 2.9078. So our answer for this interval are 0.2338 and 2.9078. Now for the second value of our y, we have sine x equals to the value of our y2. Okay, this is not y1 but y2. That's negative 0.4217. Taking the arc sine, it will give us an angle roughly equal to negative 0.4464 radians. Now from our unit circle, um, the angles that will give us a sine of negative 0.4317 are located in both quadrant 3 and 4, because the sign here are all negative. So the angle in the quadrant 4 is negative 0.4464. Okay, meaning the direction of this angle is clockwise. And then for the second spot at quadrant 3, the angle here is 3.5880. This was determined by taking the sum of pi and 0.4464. Now, the standard angle for negative 0.4464 can be expressed as the difference of, or the sum of 2 pi and negative 0.4464. That will give us 5.8368. So x here, since we are only aftering with the positive value of our x, since our interval, the numbers within the interval are all positive, so we will not use the negative 0.4464, but instead we will use its complementary angle, that's 5.8368. So the values of our x are 3.5880 and 5.8368. Combining the results, by the way, 5.8368 is still included in the interval because 2 pi is roughly equal to 6 point something. So this one is still okay. Now combine the results for both factors, or for both values of y. You have 0.2338 then 2.9078. This is for the first uh, value of our y. Then this one is for the second value of our y, still under the interval 0 to 2 pi. And all these angles are expressed in radians. Okay, so that's it for this video. I hope you learned something. Thank you and God bless.